probably known to pretty much everybody in this room. Hermann got his PhD at Utrecht. He's currently at the Department of Mathematics in Iceland, University of Iceland. He's really well known for all of his contributions to the areas of coupling, regeneration, and stationarity. In fact, there's a certain book that I think even carries that as its title, a certain very big book. So he's a authority on all of these different topics. And I visited his webpage in preparing these remarks, and I noticed there was a phrase that Hermann apparently views as being important, which is his quote, "How can you just obey?" And wasn't with the just underlined, by the way. So then I went and did a little bit of searching on the web, and that's from Emerson, Lake and Palmer, just one of his favorite groups. Is that right? Okay, so enough about Hermann. Hermann's going to tell us about unbiased shifts of Brownian motion.
Thank you, Peter. I should have used these 5 minutes to put this on. Thank you.
And Hermann has promised that he's going to finish by 3:15, by the way.
Yeah, it took away 5 minutes. So actually, this quote, it's been there now for 13 years, I think. I haven't changed the homepage. Anyway, it's a good quote. So this is the topic, unbiased shifts of Brownian motion. And actually, it's the first time I do anything on Brownian motion. This is an application of stuff that I had done with Gunther Last some years ago, and sort of general theory of this stuff, and it was done on abelian groups. So this is an application to the line. It is strongly related to work by Holroyd and Perez on allocations, invariant allocations, the myriad of Lebesgue and Poisson and stuff like that, if you have heard of that. Okay, so let's get going. What is an unbiased shift? It's do I need to turn it on? Here at the top. You think it's a computer?
Yeah. Yes. Yes. Try that.
Try now?
Yes.
Yes?
That's it. Right. Good.
Yeah. Oh, there it is. Unbiased shift. Okay, so what's the setting? We take the canonical setting, and actually, where is the highlighter? Where do I put? Sorry, how do I put the light on this?
You can just point.
Just point. Okay. So note that this is a two-sided Brownian motion, two-sided time. So let me draw Brownian motion. So it starts at 0 and somehow, and then it also goes backwards. Takis? Okay. It's a canonical framework, so no external randomization is allowed. We can't toss a coin, except maybe using the Brownian motion to do it. Okay, here is the definition. So if you shift the process, okay, a random time t is, note that it can be negative. Is an unbiased shift if the following holds: the shifted process, also shifted in space, is a standard Brownian motion and independent of the value at time t. So say that, for instance, this is t. Can you see the t? Then if you move the origin to here, then this process seen from here should be standard Brownian motion. And it should be independent of bt. Of course, yeah, you can think of this as follows. It works. So here is an alternative way of looking at this. T is an unbiased shift if the shifted process is a two-sided standard Brownian motion, modified standard Brownian motion, which is not necessarily taking the value 0 at time 0. So if we go here, then this value has some distribution, and seen from here, the Brownian motion is just going through that location on the x-axis, on the y-axis at time 0, but it's coming in from here, going on to plus infinity in time. So we can think of this unbiased Brownian shift just like this. It's a Brownian motion with a different distribution, standard Brownian motion with a different distribution at time 0, but being the Brownian forward and backward and independent, given the value at time 0. And you can also, this relates to shift coupling as follows. If we take standard Brownian motion and this modified Brownian motion with a possibly distribution at time 0, then t is a shift coupling time for the standard one and for the other one. So you shift and get the other one, if you want to look at it as coupling. So I have not completely left coupling. Okay, so let's look at examples. So a stopping time, if t is a stopping time, then if this t here is a stopping time with respect to the Brownian motion, non-negative, and the filtration f0 is generated by the past, and then growth is the one associated with the Brownian motion going forward. So it's stopping time. T is a stopping time. Then of course, the future is a Brownian motion. If you look at the one-sided future of the process, and it's also independent of the value here. If you look at it from here, but this example, the hitting time of level A. So if you take if this is A here, and this is the hitting time of A, then the two-sided Brownian motion need not be, the two-sided process seen from here need not be a Brownian motion. How can you see that? Well, since you are hitting A for the first time here, you will not be at A just before that time. But down here, there will be zeros just before time 0. So this cannot be a two-sided Brownian motion. Another example, let t be a fixed time. Then certainly the process seen from here will be Brownian motion, two-sided. But it's not independent of this bt, because you will see that if you go backwards by an amount t0, then the value of the process here will be minus bt. So bt will not be independent of the shifted process.
It seems to me that these two examples contradict the last thing that was said on the previous slide. You defined an unbiased shift, which says it's a one-sided Brownian motion going forward, i.e., that's the same thing as saying that that's a two-sided. So that remark, so is it the case, each of those two examples on the next slide, they're examples of unbiased shifts?
No, they are counterexamples.
They are
Counterexamples.
counterexamples.
Sorry for.
So each
I
of
can
those
sometimes think of
each of
counterexamples.
those is not an each
They-
of those is an example of not an unbiased shift.
Yeah, they need not. Yes, okay. So these should be. I should write counterexample, I guess.
No, it's fine. It's fine.
Okay. So these natural times are not unbiased shifts.
And we're supposed to be wondering then what the heck it could be.
Yes.
Yeah.
Yes.
Okay.
So.
And next question is, why do we need it?
Yeah.
Ah.
We may not get there.
We will see later that an unbiased shift need not be even a stopping time. Now that's curious, because part of the property is that if you go to t, the future will be a Brownian motion. So how can you have a Brownian motion if this t looks into the future? Well, you will see, but can you use it? I don't know. Okay, the case when bt is 0 is of special interest. Okay, so that's actually different from the case I drew there. So let me draw that case over here. So here you have the Brownian motion somehow. And now t is, so here is, let me try to illustrate somehow the support of the local time, the time that you, the zeros. So for instance, if t is here, so bt is 0, then in that case, the following tr is an unbiased shift. And what is this tr? Well, take some r, let it be positive, and go forward in the mass of local time until you have accumulated mass r. So r means that you go forward here until you the total mass of local time in this interval is r. It's an unbiased shift. And what does that mean? It means that the shifted process is a two-sided Brownian motion for all r. So you eat forward mass r here, and then you are here, and if then tr is a unbiased shift, which tells you, because this is 0, trivially independent of the shifted process. The thing that you see here is two-sided Brownian motion. It's just like a regenerative process. And so, when traveling in time according to the clock of local time, we always see globally a two-sided Brownian motion. Not, of course, we always see a Brownian motion ahead of us, but we see a two-sided Brownian motion also backwards. And this resolves an issue raised by who? Mandelbrot. He had all these interesting ideas. So he wrote in this fractal geometry of nature, I guess, comment on Brownian motion, on the zero set of Brownian motion, saying something like that the zeros of Brownian motion, of two-sided Brownian motion then, should be typical. All the zeros should be typical. So it shouldn't matter what zero you took, it should be, all of them, they should all be equivalent as observation points for the Brownian motion. But I didn't phrase it exactly this way, but he had the idea, but he didn't know how to formulate it. I think this is the right way to do it. Or this intuitive way of saying it. So it sort of goes back to Mandelbrot, and I became aware of this in '97, I think. David Vera Jones told me about it, and so I always wanted to look into it, and then it came in through the back door somehow. I had a theory that worked to do this, that we had been working on with Gunther Last. Okay, so we shall now sketch the theory that leads to this result and to many more results on unbiased shifts, but to no applications, right?
So again, that last sentence, we'll sketch the theory that leads to the conclusion that this is an unbiased shift.
Yes, and to many more results.
And are we going to get to of understanding some characterization of all unbiased shifts?
Yes.
Is that something?
Yes.
Yeah.
It's coming up. It's.
Yeah.
Hope you will be able to use it, but but it's all here. Okay, so now we need an excursion into sort of stepwise. We are going into Pound theory, and then we are leaving Pound theory and going into Brownian motion again. The first step is, I don't understand why I can't get a light on this.
Release your code.
Little button. Just
There's
press
a
the arrow.
long pole up there somewhere.
On the front desk.
Anyway,
There's a nice long bamboo pole.
yes, thank you. I like that. Where is it?
It's on the table. It's on the front.
Here it is. Okay. So here we add x to the Brownian motion. So now it is a two-sided Brownian motion going through x at time 0. And we denote the distribution by px. And then here comes a measure p, which is going to be a stationary measure, and you take px and integrate with respect to Lebesgue measure, and you don't get a probability measure out of that, but you get a stationary measure out of it. So under this measure, bt shifted by t has always the same distribution, that is canonical distribution p. Theta t is the shift here. So that's easy to prove. And so this is Gunther Last was extremely happy to have now real use of infinite probability measures. This is a key concept for what we are doing, even if it doesn't have a probabilistic meaning. Okay, so, and then local time, we denote by Lx, the local time at x, and they can be so defined that they are p almost everywhere diffuse, and they are invariant. So if you shift them, if you shift forward and the set backward, then you don't change anything. And local time at x can be obtained by from local time at 0 by looking at b minus x. So that's to make things sort of compatible. Okay, now into Pound theory. Recall. I hope you can recall that Pound measure, the Pound measure q psi of an invariant random measure. Invariant means that it has the property on the earlier slide, so it's actually under p, under the stationary measure p, it's going to be a stationary random measure with a sigma finite distribution. Yes, possibly. So we are actually discussing things here. We are closing in on discussing things in an abstract setup. But let's think about the Brownian motion, because we are applying it to Brownian motion. If you have some random measure, invariant random measure psi, then this is the definition of the Pound measure. And so here is the key thing. Px, which has a meaning, probabilistic meaning, Brownian motion at having value x at time 0, is the Pound probability measure of the local time random measure, lambda Lx. So what we call, in case you don't know what the Pound measure is, so here it turns out that the local time has Px is the Pound probability measure of the local time Lx. And that's important to apply the general theory that we are going to apply. And now take some probability measure nu and define p mu by this. So this can be interpreted as Brownian motion, two-sided Brownian motion having distribution nu at time 0. And create local time with respect to nu by the same integration. So it's sort of a mixture of local times. Okay. So after defining p nu this way, it turns out that p nu is the Pound probability measure of local time at nu. We call this local time at nu. Okay, and now comes the general stuff, even shift coupling. So this is general theory. On this slide, we can allow a general setting with a stationary p. In fact, B can be a spatial random field or acted on by a group. So it is a very general theory. We are going to apply it to, in this very special concrete case of a two-sided Brownian motion. So an allocation rule is defined in a way that is defined by Holroyd and Perez. This way, if you have a random time t, then you can define an associated mapping from the real line to the real line by this. And what is this? Let me explain over here. So if you have S here, and here is some here this is sort of I'm trying to indicate mass distribution random measure on the line. So here we have S, and then we move S to another location, which is by adding T of T of T of theta T circle theta S. So if you are standing here, you look at the random measure around you and the Brownian motion, and you apply T to that. T has a value if you use what you see around you as the omega, and it gives you a new location. And this map, tau, is maps the real line onto itself, and what it's doing, it's mapping the mass of the random measure into the mass of another random measure. And we say that tau balances two random measures if the image of a random measure psi is the other random measure. It's just like a distribution of a random variable. The distribution of a random variable is the image of the probability measure under the random variable.
But what is your group here? The shifts?
The shifts of indexed by the line. Okay, and here is the general theorem saying that if we have two invariant random measures, jointly stationary random measures with positive finite intensities, then they have the same intensity, and you can shift one into the other. You can shift the Brownian motion or the random field you're looking at or whatever, so that the distribution of the shift under this palm measure is the same as the distribution of B under the other palm version. And this holds if and only if this tau, the allocation, balances the two random measures. So if and only if tau maps the former into the latter. Okay, so this is a characterization that's going to be used, if and only if. Okay, now let's go back to Brownian motion, and everything should be more comfortable now.
In the previous slide, B is
Brownian motion.
here.
Yes.
Is a Brownian motion.
Yes.
Okay.
But it can be any spatial random field or whatever. Just in a canonical setting. But don't worry about the general theory. I'm posing.
Yeah, the class. Yeah. Yeah.
What?
So I can see this.
Okay, so now we are going to apply this theorem to Brownian motion. And then let's start with the Skorohod embedding problem. Of course, the whole thing is related to that problem. A random time embeds a distribution nu if the Brownian motion at time t has distribution nu. And until now, this has only been considered, as far as we know, in one-sided time, and usually t is assumed to be a stopping time. And here is our key characterization result in two-sided time. So t is an unbiased shift embedding nu if and only if the associated allocation balances Lebesgue measure at 0 and Lebesgue measure at nu. If and only if. So this is the only way to do it. And here is a proof using what we had on the earlier slide. T is an unbiased shift embedding nu even if and only if this guy here has this distribution here, as I said in the beginning. This is just a rewriting of this. And since these two things are Palm probability measures with respect to those two random measures, the shift coupling from previous slide gives us the theorem. This is what we need. This was the definition of an unbiased shift, and we have that if and only if the allocation balances the two random measures. Okay, so now let's come to something constructive. So existence of unbiased shifts. So I already told you that this guy here, TR, the one where you eat yourself amount R forward or backward in the mass of local time at 0, is an unbiased shift, and the reason, if you use the theorem on the earlier slide, the allocation rule associated with TR is this thing, and it balances local time at 0 with itself. And that's obvious, right? If you eat yourself forward amount R in the mass, you are not going to change the mass distribution. The mass is going to be the same. You are not going to another level. Okay, here is another theorem, and this is probably more interesting, even if I really like this thing. And it's the following: define a time t. Okay, now we assume this, that nu of 0, we have a probability measure with mass at 0, 0. So this is the case we are considering here. Nu of 0 is 0, while over there nu is delta 0. So these are two extreme cases. Here no mass is allowed at 0. You have to leave 0. Okay, and then define t nu this way. What does this say? Well, local time at 0 should be equal to local time at nu, at another level. And so of course, because this guy doesn't have any mass at 0, this one will have some mass in the beginning which is greater than this one. Then as t grows, there will be a first t so that they are identical. And that's our t nu. And this t nu embeds nu and is an unbiased shift. So let me try to illustrate this here. This is the level nu. You can imagine this level nu just to be one fixed state. That's a special case. Then the process. So okay. So somewhere out here we will have t nu, because here we will have accumulated some mass at nu, or at this fixed point here, which is going to be equal to the mass collected at 0. When you have collected equal mass at this level as you have collected here, then that's your stopping. It's a stopping time. Okay, and this is an unbiased shift. If we go from here to here, then we have a two-sided Brownian motion independent of this value. Remark, this stopping time was introduced by Bertrand. How do you pronounce it? Bertrand. and Le Champ, no? In 92, as a solution of the Skorohod embedding problem. So this is not a new time. It's just new in the two-sided case, where we actually show that it is also unbiased. So they proved the following. Distribution here is new, and we have a Brownian motion. That's obvious because we have a stopping time. The future is Brownian, but the distribution is new. That's what they proved. We also proved that backward you have an independent Brownian motion. And yes, okay. Here is a crucial ingredient in the proof. It's this theorem. So we had on the former slide, we had this claim that this T that I'm trying to illustrate here is an unbiased shift embedding nu, and this follows from this theorem, which is a general theorem on the line. And it says that if we do the same thing for diffuse, orthogonal, or mutually singular random measures with the same conditional intensity, that's like is the case with the two local times. Then the allocation rule defined by this, which is just copying this with the general measures instead of the local times, balances these two. And the proof, this is the hard proof in the paper. This was not easy to prove. But it's sort of something we expected by analogy, because this is what has been done in point processes and in other cases. So we were had an informed guess that this was balancing. So it was a surprise that it took so long time to actually get it to prove it. So okay, so balancing means that the associated allocation maps local time at 0 into local time at nu. Okay. One more theorem here, for 5 minutes, right?
5 minutes. There are 3.
No.
There are 3.
Yes. Here is one more, because you've seen those two. Okay, this theorem sort of dwells on the question of details. So the following holds for all probability measures. Over here we had this restriction on nu, and over there we had another restriction on nu. But here we have, for all probability measure, there is a stopping time, non-negative stopping time, which is an unbiased shift embedding nu. So you can embed any distribution stopping time-wise this way. If nu has mass less than 1 at 0, so if nu is not equal to delta 0, then all unbiased shifts embedding nu satisfy this, that t cannot be 0. Even if there is a mass at 0, you always have to leave 0 if this mass is not identical to 1. That's very strange. In order to obtain a probability measure with an atom at 0, but which is not identically delta 0, you always have to leave 0. And if nu is 0, you can actually, for every probability p in 0, 1, find an unbiased shift t, non-negative embedding nu, and satisfying that the probability of staying there is p. This was not possible here, but is possible here. And now moment properties, it's sort of optimality properties. Let me do fast. So suppose there is no mass at 0. Suppose we are in this case. And a stopping time t non-negative is an unbiased shift embedding nu. Then it has terrible moment property. The expectation of t to the 1/4 is infinite. If you are in this situation. If additionally nu has finite absolute moment, first moment, then this guy here, t nu, has the property that it's got a finite moment for all betas less than 1/4. So it is sort of as good as you can make it in that sense. And here is a theorem: if t is an unbiased shift embedding nu, not delta 0, then this is always going to be the case. And this result fits with results on matching between independent Poisson processes and the stable marriage of Lebesgue and Poisson, Holroyd and Perez, 05. These are the same. They have the same moment property there. Here is then a final moment result. If t is non-trivial unbiased shift embedding lambda 0, so it's this case over there, then it is possible that this thing this t has a very good moment property. So we are not assuming that t needs to be positive. So it can be both positive and negative. Then it can have very good moment properties. But if it is positive, and if it leaves 0, then it's going to have infinite first moment. That's regeneration, actually. Would have stationary version, probabilistic version. Okay, and minimality is the last thing. Minimality means that if S is another guy, unbiased shift, which is t is non-negative, and S is another guy of this with this property and squeezed between 0 and t, then with probability 1, then they have to be identical with probability 1. That's minimality. And this guy here, t nu, is minimal. It's as good as you can get for non-negative things. And I guess I will get this question, so I'm going to answer it. And now I'm in the question part. Okay. So we can extend this to Levy processes in a natural way, but we focused on Brownian motion because everyone knows what that is, but most people know. And here are the references, and I am done.
I'm sure that there are people in the audience that have questions for you.
Do you have your own question? In addition to the auto question. And you don't have, how about an application even in the generous mathematician sense of application?
Yes. So, thank you. In the generous mathematician sense of application. This is interesting property because it has t has this property of stopping time without necessarily being a stopping time. And so it can peek into the future and still have the stopping time property, the strong Markov property. And I can show you how to construct one just in a minute, if you would like to see.
No, just say again what you're constructing.
I'm constructing a non-stopping time t, which has this stopping time property, that it gives you Brownian motion after time t, which is a stopping time property. It's unusual that you have a time which peaks into the future, but still gives you the strong Markov property. So, according to Peter Merters, who is a specialist in Brownian, he's a mathematician, so he doesn't have probably applications of the sort you want, but he says that it is good to be freed from the stopping time need, because if you go to random fields, that's not a property which is a natural thing. But you may expect to get lots of stopping time results with times like these. That's sort of a hope for the future.
David,
Yeah, could you maybe remind us at a high level, where does the t to the 1/4, where does the 1/4 come from? I don't know.
That comes out of calculation.
Is there any kind of
I don't have any
analogy
intuition.
or-
Ask Alexander.
Yeah. Okay.
You have an explanation for that? No.
It seems
It just comes out of calculation, like much of this stuff.
pretty magical, right? I mean, it's
Yes,
kind of cool.
yes,
You get it. Yeah.
Pretty sad.
And if you have infinite mean, then so
Infinite-
if you said that if you have some finite, yes, if you finite mean that this is sharp. It's sharp.
For this guy here,
Yeah,
it is sharp.
Sharp. But if it infinite mean, if you have infinite mean that maybe even
Yes,
even
yes. Well, we don't know.
Heavier, yeah?
We don't know.
Maybe heavier. Yeah?
Yes, because then you can go very far away and you can have a bad return time because of that. Can I ask you a question?
one last question.
But I think I have asked some questions. So I
wanted to
ask
ask
a
more.
small one which you briefly touched upon. Do you know what happens for the thinner sheet? Is it possible?
For the Brownian sheet.
Yes. Yes.
Yes. Okay. So that's. So I wanted to look at that. We went to look at that, and it turned out that it's not the natural extension of Brownian motion for this kind of thing. Fractional Brownian motion.
But I'm thinking of two-dimensional time.
Yes, I'm talking about two-dimensional fractional. What is it called? You know, there are several Levy-Brownian motion.
Maybe Brian, the isotropic.
That's a different thing.
Yeah.
Yes, and that's the appropriate
Right.
one.
Okay.
Even a
That's
bigger
right.
class.
That's the one that has covariance function norm of t plus norm of s minus norm of t minus s.
Yes, but it has the right properties for this kind of stuff. The sheet is not nice because it has this, the 0 on the axis. So there is something unpleasant going on.
Yeah.
I would like to ask a question.
Hermann is going to ask.
So Hermann, do you have an example of a non-stopping time that's positive? And this unbiased? Yes, I have. So I will draw it. Okay. Okay, you can't do that. Oh, here I do it. So, no, I do it here. So, you can do it this way. Suppose you are here at 0 and here is y. And so it's not new, it's y, it's affixed to make life more understandable. So you stay at 0 for a while and then you go over here until you have enough same mass there. Then you go on until you have same mass here again. Then, wait a minute, you stay here, you eat yourself amount 1 forward in the mass here. And then you go down here and balance from here to here. Then you go back up here. Okay. Then you go backwards, maybe here, 1 amount of mass. Then you are sure to be above 0 because you have got 1 unit forward here in the mass, so you can't go below 0. And these are independent, these steps are all independent, and they preserve the Brownian motion. So this guy here is not a stopping time because it peaks into the future, but seen from here, you have standard Brownian motion going forward. That's very curious. I have no sort of naive intuition for that, but through the years, I've sort of grown some sort of unnaive intuition, so I'm not surprised.
That's a non-stopping time result I never have anticipated.
Non-anticipated result.
Let's thank both Ganesh and Hermann for really